first chapter, and that's the bounce diagrams. I'll go through this just briefly. I'm not really worried about this, but with a transmission line, if it's in steady state, if it's at a constant frequency, then the analysis that we've done so far applies to everything at a constant frequency. However, there is a transient phenomenon. I'm going to go through this one time with you. I wasn't planning on spending much time on this because honestly, it's really not something that it's more appropriate in another section we put down. So here's what they'll do. They'll put a battery here. Say it's plus or minus V naught. And there'll be some resistance here, RS. Then I'll put a switch, a simple switch like this that shuts at T equals 0. And then I'll have my transmission line. And I'll have a transmission line here. And it's going to have some load. I'm going to make this a strict real load. Then I'll just call it RL. And then there's going to be some characteristic impedance, Z naught on the transmission line. There's some phase velocity here, which we usually call C, but it can be fractions of C, phase velocity. And there's a length of the transmission line, L. So here's the question. If I throw that switch, I want to know what the voltage is here on the line for all space and all time. Now that seems like a reasonable thing to ask. And here's really what happens. Once you throw this switch, initially, there's going to be a voltage developed here that we'll talk about. And then that voltage right there acts as a wave and it propagates down, it hits here, and then some of that reflects back. And then when it hits here, some of that reflects back, and so forth, bounces around until eventually everything goes to a steady state value. Now that should seem reasonable to everybody. So here's how we go about calculating that. The first thing we do is find the voltage just inside here at T equals 0. We're going to call that V prime right there. And my V prime value, this is really at T just at 0 plus, just after the switch closed. The way we do that, well, just after the switch closed, I don't know what's at the end of that transmission line. I don't know what RL is or anything. That speed of light determined, right? I don't know. But I know what the impedance is right here, Z naught. So that V prime is actually equal to, this is V naught, is equal to V naught right there. And then it's going to be just voltage division. And it's going to be simply Z naught over Z naught plus RS. That's the source resistance, not the load resistance. Does this make sense to everybody? Just as the switch closes, the only impedance it can feel is Z naught, the characteristic impedance. So you get voltage division. Z naught over Z naught plus RS times V naught is V prime. Now V prime propagates down at the speed of light. So there's a time delay from when it starts to when it actually hits RL. And that, I'm just going to call it T delay right here. And that would be equal to the length of the line divided by the phase velocity. And that should make sense to you. If it's moving at the speed of light, it would be the length of the line in meters divided by the speed of light in meters per second. And that would give you the time delay before it hits there, right? You're going to see something called a bounce diagram in a second. Now, at this point, when it hits here, there's something called the reflection coefficient. There's going to be a reflection coefficient here. Do you remember what the reflection coefficient is? If you have just the characteristic impedance in any load, RL in this case, what is it always going to be, reflection coefficient?
Load minus characteristic over the sum of them.
Right. It's always the impedance you're going into, or in this case, RL, right? Minus the impedance you came from, Z naught, over RL plus Z naught. That's the reflection coefficient of the wave going that way. Now, when that wave hits here, the reflection coefficient times V prime is the amount that goes back. Does that make sense to everybody? I'm going to set this up it's called a bounce diagram in a second, but I want you to make sure you get your heads around what's going on. Then that reflected wave, which is going to be gamma L times V prime, comes back, and it takes a total of TD, so now we're at the second time, you might say the second TD, the second bounce. And then it hits here, and there's another reflection coefficient here, right, this one. I'll call this reflection coefficient the load, and I'll call this reflection coefficient at a source, and that's going to be the impedance I'm going into. Now listen to me on this one. Here we have to use something, remember when you had R Thevenin back in the day when you had circuits? How did you calculate R Thevenin if there was a battery in series with a resistor? For the Thevenin equivalent resistance, you shorted the battery, remember? You open the current sources. So the input impedance here is really just RS. You ignore the battery. So it would be RS minus Z0 over RS plus Z0. And that's the impedance, or excuse me, the reflection coefficient at the load. Or at the source, pardon me, the source. So here's how this bounce diagram works. We have a transmission line. What we do is this. Try to do this. This is going to be the length of the line here. And then you're going to have something here down this way. And this is going to be time, the actual time. And do you have your book? I want to show you where this is in the book. I don't usually use them. I don't want to spend too much time referencing the book on this one. I like to do it a slightly different way. But Dr. Wentworth's book, he shows this on page 87 and 88 is actually what, page 88 is the one I want to get to. All right, now, he actually calls this voltage V0, but I like to call it V prime. So this is the time, and just try to follow me on this. This is the point 0 seconds. At 0 seconds along the length of the line, we now begin something where we're going to get a bounce diagram. I have to do this. This is going to be 1 TD, 2 TD, 3 TD, 4 TD. These are all the time delays to go from one end to the other. And then 5, call this 5 TD here. And then 6 TD. And here's how this goes. Like this. All right, when I come into the line, now I have my V prime right here, right? Or I'll call it V prime. Maybe I should make this a little larger. I want to give myself a little more distance between. I got it too tight right there. I'll do this. Call this TD, 2 TD, 3 TD, 4 TD, 5 TD. Do we need 6? We'll get it. I come in right there and I call this V prime, and what I'm going to do is this. I'm going to draw a line from this corner to this corner. I mean to this point right here. And then should be right there actually. Just draw it like this. Get that one right. Call that 4 here. And we could keep going on. Now, you'll see what I'm up to in a second. As the switch closes at t equals 0, V prime is on the line. And this thing is propagating at the speed of light. Time is elapsing this way. The wave hits here. Now, the reflected value here is going to be gamma L, right, times the actual V prime. Everybody got that? That reflects back. It goes this way. And I'll show you how we get the actual the time or the voltage at any point in time. 1 second, goes this way, hits here. Then from here, this value is going to be multiplied by gamma source. So then this waveform is going to be gamma source, gamma L, times V prime. And this goes this way. Then it hits here, and again, now this voltage, which is going to be gamma L squared times gamma source times V prime, comes this way, and so forth. Do you all get the idea of what's going on, class? This is trying to just illustrate something. I know I've got to make a few more points. V prime comes on the line, it's propagating down this way. The way they do it is they have sort of they draw time on this axis, and so at TD, V prime hits here. Keep going, 2 TD, then I have the waveform coming back to this point, right? Now I'm going to show you how to use this to get a diagram of the voltage at any point on that line. So that's the length of the line total. This is Z equals 0, and this is Z equals L. And if we wanted the voltage midway, right here, let's do this point. If I want the voltage here, I'll call it Vm versus time, right in the middle. Here's how you do it. Pay attention to this. It's very easy if you pay attention, and it's very hard if you try to just wing this thing real fast. I promise you'll get confused. So the way we do it is this. I'll draw it here. This is going to be V in the middle versus time. Here's 0. We start right at the middle. This would be L over 2. And we start drawing a line straight down here. Now, exactly at TD over 2 is where I hit this first line. Do you all see that? If you think about it, it should take half the total time to go down once to get to the middle, right? So at that point, there's 0 volts, and then at the point where you're at TD over 2, all of a sudden it jumps up and it hits V prime right there. Do you all see that? And that V prime is this value, okay? Now it stays there for how long? Just think about it. Well, this is one time constant right here, right? Or one, I think you can call that a time constant or a time delay, one time delay. Then it takes another what? It's 3/2 TD right now, right? So it's going to be that way. Here's TD right here. That's when the wave gets all the way down, and then here is going to be 3/2 TD. And then at that point, what happens? Now what I have to do is add gamma L V prime to that. Do you all see that? Because this is going to be added to that. This is already there. It doesn't go away. Right? Now we have to add this to it. Does that make sense? Now what am I really doing? I'm taking gamma L V prime plus V prime, or now this value, whatever gamma prime is, I'll have to make an assumption here. I'm going to go up. Now this is going to be, this value will be gamma prime plus 1, right, times V prime. Do you all agree with that? It stays there for how long? Well, 2 TD and then what?
5/2.
That's right, 2.5 or 5/2 TD. So you get 3, that's 2 TD, and this is going to be 5/2 TD. And then what does it do? I'm going to say it goes down, I don't know. What do I have to add to it? Gamma L, gamma S V prime. You all see what I'm doing here? You see this? Can you see it over there? Everybody got that? So now, here what do I have? Now, whatever, I don't know what gamma S and gamma L are, but now I have gamma S, right, times gamma L plus gamma L plus 1 times V prime, correct? And by the way, we just keep on doing that. Now, what you're going to see is each progressive time I cross one of these points, I get an incremental change, but it's always smaller than the last one, all right? Progressively smaller, because gamma L and gamma S, the most they can be is 1. And they're usually a lot less than 1. And so it's going to keep on decaying. Now, if you would take this thing out to infinity, let me just do this over here. If I would take this waveform, and I would just go out to t equals infinity, what I'd see is the voltage that it rests to right here, V as t goes to infinity, would be equal to this. Now listen, remember how I told you a transmission line has to be equal to 1/10 of a wavelength long, at least, for it to look like a transmission line? Otherwise it looks like 2 bare pieces of wire. Y'all remember that? Well, if you think about this, as time goes to infinity, you could think in sort of this way, the wavelength is going to infinity as well. Just think about that for a second, because everything's going to a steady state, right? DC is got a wavelength of infinity. Well, then, for all intents and purposes, you can just take RL and place it right here, because now it looks like a couple of wires. When everything settles, that should make sense to you. So your final value of voltage here is just V naught, and then it's times RL over RL plus RS. It's simple voltage division, but now it's like the transmission line doesn't even exist. You just got the load connected to the actual source resistance. Everybody see that? And this is the essence of a bounce diagram. Everybody got me on this one? When you do a few of them, it'll make more sense, but you gotta understand this. Now, you can make this as complicated as you want. Sometimes you can switch on one source, and then you can switch on another. Dr. Wentworth does this. Sometimes you switch this one on for a bit, then turn it off. And there's a lot of things you can do to keep on making it more and more complicated. But this is the essence of what goes on. Now, there's one thing that people mess up that I'm gonna spend a little time on right now. You all understand this for the middle right here, right? I'm gonna do it at the end of the transmission line. So I erase this thing. I'm gonna erase it. And now, what I'm gonna do is take a look at the voltage at the end of the transmission line right here. This is gonna be at the load as a function of time. And I'm gonna do this one. This is gonna be not in the middle now, it's V at the load. Just do this. I'm going to call this TD, 2 TD, 3 TD, 4 TD, 5 TD, 6 TD, and so forth. All right, now we start here. This is real important to see this, right? It's 0 until we get to TD, and then it jumps up, right? But what does it jump to? And here's the important point. It's the superposition of the incoming and the outgoing. You all see that? The incident and the reflected pulse. So it's going to be simply, then it's right here, it's going to be V prime plus gamma L V prime. You all see that? Everybody? So at this point, at 2DD, it's going to be 0, and then it's going to jump up to V prime times 1 plus gamma L. Not just V prime, because now you got the reflected and the incident superimposed. Does everybody see that? With me on that one?
Wouldn't it be at 1 TD?
Oh, I'm sorry, 1 TD. Oh, geez, you're absolutely right. At 1 TD, absolutely right. This is V prime 1 plus gamma L at the load, right? Now keep thinking about this. Now I go back, I come back, now I strike right here, right? And I have gamma L V prime coming in, but then I have gamma S, gamma L V prime going back, right? And it comes back at 3 TD, right? Correct, class? But what do I have to do? Now I have to add this wave, right? And this wave. You all see that? So now I had this one right here. So at 3 TD, now what I'm going to have is, I'm going to say it goes up. I'm going to have this V prime times 1 plus gamma L, but then it's plus gamma L, gamma S, right? Plus gamma L squared gamma S. Do y'all see that, class? You have to add both the incoming and the outgoing at that point. They're both superimposed there. And it's going to stay there until what? Just help me out here. How long is this going to stay there? And then what happens? I don't have it shown there. What am I going to add? Well, now I have this waveform, right, coming back, hitting the source, so it's going to be gamma S squared gamma L. Then it comes back, and I'm going to have gamma L cubed gamma S squared, and then I'm going to have, wait a second, I'm just going to have gamma L squared gamma S squared plus gamma L cubed gamma S squared coming back. And by that time, usually these values like gamma L and gamma S are 1/4, 1/2 maybe. Well, when you start getting into them squared, think about 1/2 squared times 1/4 squared, right? That's 1/16 times 1/4, 1/64. It's getting to a point where it's pretty much no change. Do you follow me? It asymptotically just goes to 0. I'll say one thing about this. Right here is the problem. A lot of people mess this up right at that edge because they forget to take the incoming and the outgoing. They're only looking for one. Remember that. And that's pretty much bounce diagram in a nutshell. And that's about all I have to say about it. If you have a question about it, let me know. I'll give you some problems. But it's not hard. And it's perfectly logical. There's nothing tricky here. You flip a switch, the pulse goes down, bang, 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 bang. It's echoing. All right? All right, now, Now we're done with chapter 2. And now we're gonna get into electrostatics. I kind of like the way Dr. Wentworth's book first goes into transmission lines, because everybody here is familiar with resistors, capacitors, and inductors. So it's a natural kind of thing to do. It's still fresh in your mind from your circuits courses. Y'all should have had circuits last semester, probably. Did y'all have that? No? How many semesters ago?
4, 3 or 4.
For real? This is usually right after circuits. I thought in the way it's cataloged, isn't it? Or not? No?
It's a suggestion.
Yeah. Oh, you do signals first, right?
Yeah.
Okay. Well, signals and systems, you need circuits too. All right, now with electrostatics, let me give you a little background on this one. I kind of go through this. Everything that we know about electromagnetics in general, and physics overall, is based on measurement. Mathematics is the way we describe things. It's our language of description and exactness. But it's always by experimental measurements. That's the only way we know any of this. There's not, 10 commandments that came down a mountain, and, curly is equal to this. It's not. So remember, all these are based on measurements. So when you're measuring something, you have to have a force pushing something, where you can measure like the displacement of a spring or something like that. All right, so the first law is the most logical, is Coulomb's law. And Coulomb's law has to do with 2 charges. So you can write this down, or any number of charges. We're going to start with 2. So if you have a charge Q1, and you have a charge Q2, and the charges are, by the way, in coulombs, who would have saw that one coming? It's his law. And they're separated by some distance. I'm going to call this, actually, for 1 to 2, I'm going to call this R, a vector R. Now, vector R has magnitude and direction. I'll get to that in a second. Then I'm going to say that the force on charge 2 caused by charge 1 is equal to Q1 times Q2. Now, we're multiplying the charges. Remember, they have signs, so it could be a plus and a minus, or 2 plus or 2 minuses. Remember that. And the general law the general rule of thumb is opposites opposites attract, likes repel. So Q1, Q2, then you have this. You'll have 4 pi epsilon naught. This is the first time you see epsilon naught here, times the magnitude of the vector R squared times a unit vector AR, and it's in the direction from 1 to 2. Now I'm going to get to this in a second. Epsilon naught is called the permittivity. Permittivity of free space. You saw that constant shown in physics, I'm sure, right? And your the actual electricity part of physics, epsilon naught. Now Q1 and Q2 are in coulombs. R is in meters squared. Now when I have a vector R, in general, please watch this. A vector R in general, you're going to have some value, I'll call it A1 AX plus A2 AY plus A3 AZ. Now that just means AX is just a unit vector in the direction of the x-axis. AY is a unit vector in the direction of the y-axis, and AZ is a unit vector in the direction of the z-axis. Do you follow me on this, class? R just represents the scale factors A1, A2, and A3 are just any scale factors. It could be 3AX, 0AY, 1AZ. Could be anything, but that defines a vector from one point to another. Remember, direct vectors have magnitude and direction. To get the magnitude of R, how do I do it? Anyone? How do you get magnitude of anything? If you got, this is an orthogonal system.
Square root of A1 squared plus A2
You
squared.
square each of the components, add them together, take the square root of everything. You're absolutely right. So it's the square root of A1 squared plus A2 squared plus A3 squared. You all agree with that? Now this is important. To get that unit vector, AR12, what you do is take R vector, remember this is gonna be a vector going from 1 to 2. I'll call it R, 1, 2. It's a vector, and you divide it by the magnitude of R. That will give you a unit vector. A unit vector means it has a length of 1, only 1. And that's a unit vector. And that's basically Coulomb's law in a nutshell. If you want to, we'll do a simple one in a second. That's for just 2 charges. But you can have as many charges as you want. If I put another charge here, call it Q3, and I'll call this R12, and suppose I had an R32 here, then there would be a force, let me just say this, from Q1 to Q2 there's a force, I'll call this F12, and then from Q3 to Q2 there's a force that would be F32, and the total force would be the superposition of these. Do y'all see this, class? And no matter how many charges you have in there, you can calculate the force on that charge by each of the individuals, then sum them vectorially, and that would be the total force. Did you follow me? And that works. I'm going to do one simple problem to give you an idea of the force. By the way, do you know what the conversion is from newtons? Newton is when we talk about force, Newton is a force. Do you agree? Right? What's the conversion into Newton to, say, pounds at the Earth's surface? Do you know? You can Google it. If you can check it. I think it's about 5 point something, but just check what it is. Anyway, what I wanted to do is give you an idea of how much force goes on, because here's the actual experiment. What they did is have a string of length L, and they had 2 charges, identical charges, call them Q and Q. But there was a separation here of D, and that means there was a force in this direction, a force of this direction, and the force in this direction would be equal to Q squared over 4 pi epsilon naught D squared, and that would be in this direction. Do y'all follow me on this one, class? Now, these pith balls right here have a mass M, or whatever they are. I say the pith balls. They could be chunks of metal. All right. That mass M is causing what? Because of gravity, it's undergoing a force this way, M times G. Do you agree with me? Straight down. But there's something that's holding it there, so it doesn't just take off this way, and that's the force on the string. And that string has an angle here of theta, which means from here to here, it's theta over 2. Does that make sense to everybody? Let's do this problem. I'll even put in some values in a second. But if we had the general thing like that, this is a typical physics problem, isn't it, guys? I mean, this looks like something right out of your physics book. Well, how do you do this? I know that mg I've got down. I got that, right? All right, now, when I take a look at this to do my force triangle, this is mg, right? This is going to be, I'll just call this F electric, right? And then I have this right here, right? Well, what is this composed of? That's a bad drawing. Remember, nothing's moving, so the sum of forces is 0, right? Well, what do I know? I know that this force in this direction has to be Fe as well on that string, right? And the vertical has to be mg, so that this would be the force decomposed, right? Isn't that right? Now, we know this angle right here, that's theta over 2, right? Right. So we can get, based on that, if you look at this, if this is mg, is an opposite over adjacent would be equal to the tangent of theta over 2, right? So opposite is F on the charge, or just call it F right there, divided by mg, that's the force in this direction, would be equal to the tangent of theta over 2. Agreed, class? Now this F right here is this Q squared over 4 pi epsilon naught D squared, right? Now what we're going to do is figure out what the charge is on there, but I'm going to give you some values, all right? Remember, mass, when you do MKS systems, is always in kilograms, right? So we're going to talk about the mass here, mass being equal to 0.001 kilograms. That's still kind of heavy. G, by the way, is what? 9.8 meters per second squared. Do you agree with me there? Or G or A, in this case, however you have it in physics. So I have that. I'm going to say that the half angle over 2 was equal to 1 degree, no, 2 degrees, 2 degrees, all right? So can you guys get your calculators out and just give me what the actual force is? That would be M times G, or it's really 10 to the minus 3 times 9.8. Right? Then it's going to be the tan of theta over 2, so it would be 1 degree. And what is that going to be? Small.
0.342.
Is that right?
Or,
That's 10 to the minus
well,
third.
sorry, yeah, 0.342 times 10 to the minus third.
0.342 times 10 to the minus third, right? You guys getting that? Josh?
Are you wanting the angle to be one, you said
It's theta
over
is
two.
theta is actually 2 degrees if, oh, I'm sorry. You're right. How about we make this 1 degree? That's where I was shooting for 1 degree in there, so make it 1 degree.
It'd be 0.173, or 0.171, sorry.
0.171, thank you.
E to the negative third.
0.171 times 10 to the minus 3, correct? I want it to be 1 degree in the tangent argument. That's what I'm getting at. Now that's equal to this stuff, q squared over 4 pi epsilon on d squared. I'm going to make the separation d right here equal to equal to 1 centimeter, 0.1 meters. So that's going to be d. And that means this is equal to q squared, right, over 4 pi epsilon naught d squared. Now here's what I'm going to do next. Y'all agree with me so far? I'm going to take this quantity and multiply that quantity and then take the square root to get q. So q would be equal to the square root of, I'll call it 1.71 times 10 to the minus 4 times 4 pi times epsilon naught. And I got to give you a value for epsilon naught. There's 2 that I like. Epsilon naught can be rendered as 8.854 times 10 to the minus 12, and that's farads per meter, or it can be equal to 1 over 36 pi times 10 to the minus 9 farads per meter. This is used a lot because the pi's cancel them. And if I do that, I have 1 over 36 pi times 10 to the minus 9. And then I have d squared, which would make it 10 to the minus 2 times 10 to the minus 2. And that would be equal to q. So what do you get for q when you do this? The 4 pi over 36 pi is really 1/9.
Times 10 to the negative 14. Oh, sorry, that's not square rooted. 1.38 times 10 to the negative 7.
And that would be coulombs. So it's 0.138 microcoulombs. Follow me? Now that's not too far from the actual way the experiment was done in the first place. They had a known weight, a known mass. At the Earth's surface, gravity is about 9.8 meters per second squared. And they could then determine what the charge was. There's more to this, but you all see how this is a simple experiment. If you have an accurate measurement system where just the deflection gives you the actual value of charge, and the larger the value of charge, the greater the deflection, or the more the angle would be where they spread apart. You all see this? Do you remember this, by the way, in physics when they did this one? This is the classic. All right. That's a unit vector, this is the force law, and this is an experiment. And this is one that is, this kind of thing is typically asked in physics courses. In engineering, we ask something like that. Dr. Wentworth has a question like that in the back. And it just gets you thinking about other aspects of physics where you have now kinematics coming in, where you have mass times really acceleration, you get a force. And I asked this question, what was Newton's relationship to pounds, by the way?
It's 4.448.
For newtons to a pound?
Yeah.
Yeah, and I thought, I keep remembering 5, but it's 4.448, which is 4.5. So a lot of times if we're gonna calculate forces in newtons, I change them to pounds because I think in terms of pounds. I go over there and lift weights, I know what 150 pounds feels like. I don't know what 150 newtons feels like, not off the top of my head. But it's reduced by about a factor of 5 is the way I used to think of it. So, or I'm sorry, it's 5 times as many newtons as pounds. So 100 pounds is 500, 450 newtons, something like that. And I've noticed one thing of late, more and more, the plates I'm seeing being sold and being used are now in kilograms. They use real mass, they don't use pounds, which is a force. They use just mass. I don't know if you see this very often. They got kilograms, like 20 kilogram plates and stuff like this instead of 40. Well, yeah, instead of 45 pound plates. All right. Now, here's the next step. After we define the electric field, I have some other notes about this. You all have had vectors, right? Dr. Wentworth's book goes through a little deal about the different coordinate systems and different vectors. I'm going to get to that when I need it in a second. But have you all had cylindrical coordinate systems, right? Have you had spherical or not? No? All right, I'll work you through it. I'll show you how that's done. But before I do, let me go to the next step. Instead of saying that, in general, when we want the force on a particle or force on an object, saying it's equal to the sum of Qn times Q, call it A, QA, over 4 pi epsilon naught, and then it's going to be R A to N vector squared times AR, A to N, unit vector in that direction, and doing the sum over N equals, say, 0 to N minus 1, where N minus 1 charges are outside the original charge. You don't have to pay attention to this. What I'm really saying is this is a summation symbol. So if you had more than one charge, you would keep on summing the forces, but you would always have to do this multiplying, right? Q1 times Q, whatever the charge there is times the charge there. Well, there's a way to get around that. Force, in general, is equal to charge, Q, times something we would call the electrostatic field, E. Now, this is a basic physical concept, but force can be given as an electric field strength times Q. And Q would be the charge where the force is developed. The electric field, E, is in volts per meter for our class. There's other English units, but we use volts per meter. And it is both it's a vector, so it has a magnitude and a direction. Q is in coulombs. I'll just put that down. Q is in coulombs. Which it means is that E in general can be gotten from the force on any charge divided by the value of the charge. And what that does is exempt us from worrying about the actual value of the charge at that point. What I can do is calculate the electric field in any charge that I introduce there. I can calculate the force on it by multiplying it by the electric field. So, this is the one I wanted to focus on. If you want the electric field at any point in space, E here, and you had an assortment of charges called Q1, Q2, Q3 here, and you had some distance, I'll call it R1, distance, a distance R2, and a distance R3 here. These are all vectors, by the way. Then I could say E here is really going to be equal to just Q1 over 4 pi epsilon naught, and then it would be R1 magnitude squared, AR1 plus Q2 over 4 pi epsilon naught magnitude of R2 squared, AR2, plus Q3 over 4 pi epsilon naught magnitude of R3 squared, AR3, and so forth. And you could write this in terms of a sum, but I'm just saying now you take a look at the electric field components from each of those things, add them vectorially, and it has to be added vectorially. Follow me on this, class? We could do a problem like this, but this is really not tricky at all. The only thing you need to do is make sure you get the vectors right in terms of the direction, the unit vectors in terms of the direction. And for that, I suppose I should do one short example. So we'll work right here. This is kind of boring, but it's important. Yeah, everybody sees me. If we're in Cartesian coordinates, if this is x, y, and z, and I have a charge, and the charge is going to be located at 3x and 2y, and it's out here, and I'm going to try to draw this for you. And say I have a charge equal to 1 Coulomb right here. Now this is a typical question, so pay attention. Now it's going to get a little more complicated. But, so the charge is located at 3x, this is located at 3x, 4y, and 0z. The way it's always rendered in points is x point, y point, z point. It's the actual value of the on the coordinate axis. So 3, 4, 0 is right there in the plane of z equals 0. And if I want the force at z equal 5, or the electric field at 0, 0, 5, I want that field. Well, what would it be? E at 0, 0, 5 would be equal to, first it's the charge, well that's 1 Coulomb, that was nice of me, over 4 pi epsilon naught. Now I need this distance, and this is the one people mess up. I need that distance, that's R1, isn't it? So how do you always get distance between 2 points? Here's the point I'm starting at, here's the point I'm ending up at, right? You always take the coordinates of the point you end up at minus the coordinates of the point you came from, right? And multiply it by the actual component, vector component, unit vector component. So for this one, the vector R, I'll put it here, would be what? R1 would be, in terms of x, what's the x coordinate here? Class?
0,
And what's the x here?
3.
So it's going to be minus 3 ax, you follow me? 0 minus 3. For the y component, it's what? Y component here?
0,
Y component here?
4.
So it'd be minus 4, right? Az, or ay. What about az? It would be
5.
4 plus 5z, right? So that would be R1, correct? And what would a unit vector be in the direction? AR1 would be equal to, well, it's this vector divided by the magnitude, so it's minus 3ax minus 4ay plus 5az divided by the magnitude of that, which would be square root of what? 9 plus 16 plus 25. Y'all follow me? Now, you would simply take the magnitude here and square it, and you'll notice when you take the magnitude and square it, you just get the quantity 9 plus 16 plus 25 here. And then, I'll just put 1 there, you multiply it by that AR1, and that would be the electric field at that point. And you can see it's a little bit of bookkeeping here for exactness, right? You gotta be careful with that. Something I'll tell everybody, and a lot of times in general physics and stuff like this, they don't really focus on being exact with the calculations. This is my opinion, I could be wrong about this, but it's always seemed that way. In engineering, it's a big focus, because in engineering you build stuff, and everything has to be precise and exact, or things don't work. So precision in these calculations and getting it right is very important. Even though it seems rather trivial, and you can easily get bored and not want to do it. All right, that's sort of the electric field in a nutshell. And then, now this is the one thing I have to do, because so far I've been talking about the electric field in terms of just chunks of charge defined, right? But that's not what we really have. We have continuums of charge. We have a line of charge, right? Or we have a surface of charge, or a whole chunk, a sphere filled with charge, right? So now what we have to do is define what the electric field is from a differential charge, and then expand it and calculate what the electric field would be like from a line of charge. So I'm going to do that next. And then we'll introduce different coordinate systems. This should be fairly old hat to you, this stuff right here. You've seen this in physics. I don't think you saw transmission lines in physics, though. Did you? Did you have wave guides of any type, like echoing guides or anything like that? Sonic guide? No. Okay, next, we're going to say this is a natural extension. It should make sense to you. If I have just a differential chunk of charge, dq here, d is differential, and I want to know at a given distance r what the differential electric field was here, that would simply be dq over 4 pi epsilon naught r squared, that's a vector, times ar, a unit vector in the direction coming from the charge pointing at the electric field. Does that make sense to everybody? If a whole charge Q gives me a whole field E in a sense, then a differential charge gives me a differential electric field. Now here's why I say this. Suppose I have a line of charge, an infinite line of charge. Or better, yeah, I'm going to go ahead with an infinite first. And this infinite line of charge is on the z-axis, so put that down. And the actual charge on this is going to be rho L. And rho L is in coulombs per meter. So it has so many coulombs per meter. Now what I'm going to do, this is the z-axis. I'm going to say this is the origin, this is x, and this is y. And what I'm going to do is come out a distance on the y-axis. And I'll just call this 2y. Why don't I just use this? This is the y-axis here. My distance here will just be y. And I want to calculate the electric field at this point. So I want to know what the electric field is here. That seems like a reasonable request. It's got an infinite line of charge. There are some, in the real world, this approximation isn't too bad. And I'll tell you when. Suppose I have a wire above me, and I know it's picking up electrical charge, and let's assume it's about homogeneously distributed on that wire. That's usually the case, by the way, because like charges repel, and they tend to push each other away, so there's about an even charge density. That's the way it is. But I'm not very far away. I'm literally on top of it, so maybe I've got half an inch between me and the wire, and the thing is meters long. It looks infinite at that range to me. That's where this calculation would have meaning. This is an estimate of the electric field strength there. So how would you do it? You start by taking a differential chunk of charge. So I'm going to just take a differential chunk of charge here. That's going to be dq, right? And I'll call that rho L, that's the line charge density, times the dz axis, times dz. And that should be a differential chunk of charge within dz. Does that make sense to everybody? Now this is at a height z. I'm going to say this is going to be at some height z. This is where it's important. Now, if we go from here to here, I have an electric field, a differential electric field in this direction. Don't I, class? Right? So to get that field, what do I need? I need this vector r. And that vector r would be in Cartesian coordinates. It would be the difference in the x coordinate, which is what? 0 on purpose, 0. Right? Then we take the difference in the y. Well, this value of y is 0, correct? And this is going to be at y, so it's going to be minus y, ay, correct? 0 minus y. And then the difference in z, which is Z coordinate here?
0.
Minus Z, so it's minus ZAZ. So that's the value of R, right there. From this point to that point. That means, then I can say that AR, right, would be equal to minus Y AY minus Z AZ divided by square root of Y squared plus Z squared. Y'all agree with that? Now what I need to do is say that my differential electric field here would be equal to rho L dz, that's Q, that's the differential charge, rho L dz, rho L's a constant, over 4 pi epsilon naught, and then it's going to be times this distance squared, so it's going to be y squared plus z squared, right? That, I mean, the distance r here, if you get the magnitude, is square root of y squared plus z squared. If you square that, you get y squared plus z squared. And then it's times this unit vector. Now you'll notice this about this unit vector. You see how the denominator has y squared plus z squared to the 1/2 power? What I can do is take this and just make it to the 3/2 power right here, and then put minus y ay minus z az. And that would be the differential electric field from that point, correct? But we don't want it from that point only. We want it from every point on that axis. So what am I going to do? What's the word I'm looking for?
Integrate.
Integrated. I'm going to integrate this thing from minus infinity to infinity to get my total electric field E. And voila. The total electric field is given as such. Now, here's where a trick comes in. Well, really, a shortcut. You're going to have to pay attention to this one. I'll let you stop writing so you can see it, because it's a good shortcut. It's something engineers take note of and use all the time. When you see something obvious, a symmetry that you can exploit to reduce the complexity of a problem, do it. Do you all agree that if I have a charge here of rho L dz, if I come down the same distance z here, I also have the charge rho L dz here. Same exact thing, don't I? And this would have what? It would cause a force to be in this direction, or an electric field, a differential electric field in that direction, right? By this time you see it. Do you all see what I'm talking about? Well, if I add this one plus this one, don't the vertical components cancel? I'm left with only a radial component. Do you all see that? Or a component pushing away, which is the y component, which is nice, which means effectively I can do this. I can eliminate, I know I'm only going to have a y component, this z component completely. I know it goes away. You follow me on that one? And then instead of going from minus infinity to infinity, I can just go from 0 to infinity and put a 2 out here. In other words, I'm going to integrate from here to here, but I'm going to double the actual value of the y component, because that would be the same amount added by this bottom part. You all see that, class? So now I've got to do this integration. And when I look at this, I have E equal to 2 rho L over 4 pi epsilon naught, and then there's a minus sign here. And then I have the integration of, really the y is a constant, so y can come out front. The integration of 1 over y squared plus z squared to the 3/2 power from 0 to infinity, and it's integrated dz. Let me make this a little nicer. So this is going to be y squared plus z squared to the 3/2 power. Do you all agree with me there? And I got to go dz. Now, something about this right here, this type of an integration occurs all the time, and I believe I can set, since y squared is a constant, y squared plus z squared to a constant, you could call it r squared, and then the derivative just think about this for a second. So that would be equal to rho L over 2 pi epsilon naught y, and it would be in the AY direction. And how I got it would be to take anyway, this integration would be that, r squared to the 3/2 r that cubed. And this is what it will come down to when it's done. In his book, you have that book, I'll show you one thing about these integrations. You usually use trig identities to do these. I haven't done that in a while, but he has in the back of his book, yeah, he's gonna have that one right there. And that's like the 5th or 6th integral down on page 623. He has the basic integrals there. I think this is actually this is a trig identity integration. And I'm not gonna even bother messing with it right now. But anyway, this is what it'll come down to. Rho L over 2 pi epsilon naught y. Y'all follow me in this class? We can do the integral if you want, but I think it's kind of a waste of time for this.
Are we gonna be given like this? Or do we need to know all these? Or we
No,
gonna
no.
get-
You'll need to know this in basic integrations, but something like that I would provide. And I don't ask you to know anything higher order. Everybody okay with that right here? Now, that's the electric field from an infinite line charge. The next thing that's a logical step to do is what would be the electric field from this? Suppose I have, this is X, this is Y, this is Z, and suppose I have a ring, a thin ring with a charge density rho L. Now I take a wire and bend it into a loop, and I want to know the electric field on the Z-axis anyway. All right, for this one, we're going to introduce the new coordinate systems, which will be cylindrical coordinate systems. Then we'll talk about spherical. Now, you've had cylindrical before. I'm not sure if you called it cylindrical. You might have called it polar, something like that. So I'm going to go ahead and erase this. We're going to address that problem, but first I need to bring you up to speed with the actual coordinate systems and unit vectors in that coordinate system. And I also have to talk about the differential length, differential surface, and differential volume in each of the coordinate systems in order to do this. This is something in physics you talked about a little, but you probably didn't spend a whole lot of time on it. And I want to show you where that is in your book. We just did, I think he talks about coordinate systems back here.
Yeah, that's fine. Spherical.
Not spherical, I want cylindrical. He does spherical first, and I don't like that. Cylindrical is right here. So when we talk about cylindrically symmetric systems, or when cylindrical symmetry makes sense to use is when there's cylindrical symmetry. So everything is cylindrical or is symmetric about the z-axis usually. Now what they do is this. They first put in a Cartesian coordinate grid, x and y, and this is 80. And then what they'll do is this. They'll say that now we're going to introduce something different. Instead of having coordinates that have x, comma, y, comma, z designations, what we're going to do is have one that has a radial distance rho measured from the z-axis, where there'll be an x coordinate right here and a y coordinate here, such that rho would be equal to the square root of x squared plus y squared. It has no, z is not a function of this. This is anywhere up and down the z-axis. It's the radial distance from the z-axis to the point x, y at any height z. Follow me? And it's the shortest distance to the z-axis. Think of that from the point. Now there's also an angle, make sure you see this. There's an angle measured from the positive x-axis to that radius vector rho, and that angle is designated phi. Now if you look at that for a second, phi can be gotten, if I do it this way, you'll see it easier. I'll pull this, I'll look right down the z-axis. This is x and this is y. And here's my point here. And this is phi, right? Then what I can say is that phi would be the opposite, this would be the y distance, over the adjacent equal tan phi, or phi would be equal to the tangent minus 1 of y over x. That should make sense to everybody, right? So the way it goes is we designate things with the value rho, phi, and z. And z is the same thing as in Cartesian. So these points translate to rho, phi, and z. If we're talking about going from Cartesian to cylindrical. Got it, everyone? Y'all see this right here? It's just it's another way of stating a location of a point, but in a different system. It's cylindrical symmetry, or cylindrical coordinates, all right? Now here's where it's important. I didn't talk about this yet. When I talk about differential length, dl is differential length. dl is a vector, and it's usually dx plus dy plus dz if we're in Cartesian coordinates, and that should make sense. A differential length has a certain amount of change in the x, certain amount in the y, certain amount in the z. Do you follow me, class? Cartesian is a little different. You've got to pay attention to this. I mean, sorry. The differential length, that's in cylindrical, in Cartesian coordinates. This is x, y, z coordinates. When we're talking about rho, phi, and z coordinates, then the differential length becomes, it's going to be d rho, a rho, and I'll try to show you why it's that way. All right, if we're moving, we're going to move some d rho, a rho, right? But when I'm moving in this direction, when I think about this, which is in the a phi direction, I didn't mention this, by the way. When I talk about a unit vector ax, it's a vector. Ax is in the x direction. That's a unit vector. When I talk about ay here, ay is a unit vector in the y direction, just a unit value 1 ay. And az would just be 1 az. But when we talk about unit vectors in cylindrical coordinates, the actual unit vector a rho is in the radially outward direction. Now a rho by itself, if you look at that, it depends on the angle which way it's pointing, right? The definition of the angular point tells me which way a rho really is pointing. In Cartesian coordinates, ax is always ax, it never changes. But in cylindrical coordinates, a rho, in a sense, changes its angular orientation. Its magnitude never changes. Do you follow me? And it is always radially away from the z-axis, but where it is another thing. I mean, its actual angular orientation. Then when we talk about a phi, this is the one I want you to see. A phi, well, think about this. If you take this, the way they usually say is you take this and now have a differential phi change. What happens? This is the direction it would move, right? But it would be multiplied by this length, rho. So when I take a look at this, the differential arc length would be plus rho d phi a phi plus dz az. And the key thing I want you to see is the value, it's not just d phi a phi, it's rho d phi, because the length of that vector rho, how far away you are, determines for a small angle d phi how much actual deflection occurs, right? The longer it is, think about just, the hands of a clock. Well, if the hands are 1 meter long and it ticks from, say, 0 to the 1 minute mark, it moves a certain length. If it's 1,000 meters long, it moves that length times 1,000. Do you follow me? The actual tip of that thing would move. So that's important to know. That's the differential length in cylindrical coordinates. We call these cylindrical. I'm not going to put spherical down yet. Now that's a length. There's also something called a differential surface. So when you have a differential surface, I always have to tell people, I'll start with Cartesian coordinates and just put a box here. This is going to be differential surface. That's length and surface. When I take a look at ds in general, you have to follow me on this one. If this is, let me do it this way, call I just want to go this way, out of the paper x, out of the board x, in this direction y, and up z, all right? Now, a cube has 6 sides to it. Please watch this. X is out of the board, or out of the whiteboard in this case. Y is in the plane but going that way, z is in the plane but going up. If I look at this surface of the cube, right here, I see it has an area of dz, dy. So right here, it would be dz, dy. Follow me? But it has to have a vector sense, and I want you to listen to me. What we do is take your right hand and grab that, all right? And the direction your thumb points, it's got to be a rotation as if it's closing the door, right, in the plane of the board. Your thumb points in the unit vector sense of that. So it's dz, dy in terms of its magnitude, and it would be ax in terms of its surface vector. It's pointing outside, away from the interior of the cube. Does that make sense? Now, if you're on the other side of that cube, we'd still have an area of differential, this is the differential surface, ds. It would still have a differential surface of dz, dy, but then it would be minus ax. Does that make sense? Now it's pointing in the other direction. Follow me? The differential surface is always pointing away from the surface within a closed region. It's pointing outward, outward from the closed region. What would the differential surface be here? On the top, ds would be what? Well, what's this differential?
dy.
And what's this one?
Yeah.
dx, so it's dx, dy, right? And what would the vector sense be?
AZ.
Positive az, right? What about in the lower surface if we were down here? Magnitude would be,
dx, dy.
and vector sense?
Minus
Minus az, right. What about this surface right here? What's the differentials?
dx, dz,
X, dz, right? Go ahead.
ay.
And positive ay. All right, I think you guys get it, right? That's what they would be for Cartesian differential surface. And you see, I can't just write one equation. There's 6 sides to this thing, so there's 6 possible values of ds. You follow me on this? Now when we talk about the differential surface here, I'm going to do this it's going to be now in cylindrical coordinates. Now ds gets interesting. And let me do it right here. Now when we take a differential surface, in general we have to do this. Matter of fact, let me do it right here. When you take a look at this, this is x, y, z. And I'm going to put a big can in here so you understand why I'm doing it. Well, in general, if you have a can, right? You have 3 possible surfaces. There may be more, but you have this outer surface of the can, right? The curvature. Then you have the top of the can and the bottom of the can, right? You follow me? Now, if we're in cylindrical coordinates, if we go to the top of the can here and we look at the differential surface, well, we're going to have some, let me try to draw it here. There's going to be some d rho here, but then there's going to be this value here, which is rho d phi, right? You all see that? It's like the wiper on. I'm trying to make this as much of a square as I can, but there's a differential going outward. That's just d rho. It's like dx. And then there's this orthogonal one, rho d phi, that way. And that makes a little patch, ideally a square differential patch, right? But what's the direction?
az.
Z. So this differential surface right here on the top would be equal to rho, then it would be d phi d rho, right? AZ. What about the differential surface down here at the bottom of this can? ds would be what? Rho d phi, right? D rho minus AZ, right? It's pointing downward, right? Y'all see this? Now what about on the surface of this can? Well, I'm trying to show you. This length would be equal to rho d phi. You all see that? It's the outer edge, right? It's like, this is still dz, and it's pointing in what direction? A rho. It's pointing radially outward. You follow me? Can you see that? The differential unit vector would be pointing out. So here on the surface here, ds would be equal to rho d phi d rho a rho. Are you with me? Finally, so I'm drawing it right there. You can see that there are 3 possible differential surfaces depending on the location you're talking about, right? You could probably even make more if we cored that thing out so there was an inner cylinder in there. Then we could say the differential surface on the inner core would be the same as the outer core except minus a rho. You follow me on that one? Now, so those are the differential surfaces. Now differential volume, and this is going to be an x, y, z. Differential volume is the easy one. It just multiply the differentials. So it's simply dx, dy, dz if you're in Cartesian coordinates. It's just a box. What's the height of the sides of the box? dx, dy, dz. And if we're in cylindrical coordinates in rho, phi, and z, then the differential unit of volume is going to be equal to rho d phi times d rho times dz. And that's the differential unit of volume. I'm out of time, am I not? Sorry about that. And we'll pick up cylindrical coordinates next time, and I'll give you some homework. If you have questions about the quizzes, see me, and I'll be upstairs.